You know, densities tell us the relationship mass and volume, mass to volume ratio. And so if the mass of 1 liter, 1.000 liters of gas is 1.436 grams, then that means there's 1.436 grams of matter for every 1 liter to 4 sig figs. And so this is the density. Well, what would 1,000 milliliters of water weigh? 1,000 milliliters of water should weigh 1,000 kilograms. And so this is about 1,000 times less dense than water. So gases are roughly 1,000 times less dense than water. And so we could use that density. So for example, if we only had 0.0573 liters, well, that's going to weigh a lot less. So this is what the calculation was about. We looked at 6 big. And so here's the density relationship here. That's our given. This would be our conversion factor. We're using density as a conversion factor to get the mass. We could also use density as a conversion factor if we flip it over to get the volume. So if we're given a mass, we can figure out its volume. Density is a very common conversion factor that we use over and over in science, so it's very common. All right, we use the USCS units, United States Customary System, in which we deal with inches, pounds, and gallons. This one you have to have memorized. You know how many centimeters are in an inch? About 2.54 or exactly 2.54? About 2. No, exactly. Yeah, it's very odd. But it's exactly to infinite number of sig figs. So there's exactly 2.54 inches. Now, this is the definition of a pound. A pound is 453.59237 in terms of grams. Do you want to memorize all those? No. So instead, we say, we know this to 4 sig figs. So we say that 1 pound is approximately 453.6 grams. And so that's the usual conversion factor. 4 sig figs is usually enough. So in exactly 1 pound, there's approximately 453.6 grams. And the same thing with volume. We usually use this to 4 sig figs. And so in exactly 1 gallon, there's approximately 3.785 liters. I said 4 liters yesterday, so it's quite a bit off. You know, it's actually 3.785 liters, or around 3.8 liters. Depends on how precise you want to get. You know, the more precise you are on these, the better accuracy you're going to have in your calculation. And so even though these 3 are exact, we only learn 1. This one. The other 2 here, we'll just use the 4 sig figs. These are exact. You know, 12 inches, exactly 1 foot. 3 feet, 1 yard. Exactly 5,280 feet is 1 mile. So these are all exact. 16 ounces, 1 pound. 32 fluid ounces is 1 quart. 4 quarts to a gallon. All these are exact. So they all have how many sig figs? Infinite sig figs. These are in the book.
The triple equal sign, does that mean exact?
That means exact or by definition. That's what the triple equal sign. Well, anyway, these are the ones you're supposed to learn or how to learn. But a soft drink manufacturer is converting from USCS units to metric units. If the quart bottle initially is to remain at the same volume, what number of milliliters should be printed on the label? And so we want to know how many milliliters are there in a quart. And so should we say approximately 1 quart? If we say approximately 1 quart, then that's anywhere between half a quart and 1.4 quarts. Does it make sense to say approximately 1 quart? No. And so in this case, we're going to say in exactly 1 quart, because otherwise it just gets too blurry. And so if we leave it exactly 1 quart, then approximately how many milliliters are there in exactly 1 quart? That makes more sense, right, to do. And so what we need is we need something to get rid of quarts. You know, this is the dimensional analysis approach. I don't know which way I'm going to go, but I need something that gets rid of quarts. So think of what you have memorized. We can convert quarts into cups. We can convert quarts into gallons. Which way do you want to go? Should we go quarts to fluid ounces? 32. I don't know the conversion. Well, it is 32 fluid ounces, but I would go quarts to pints, and then 1 pint is 16 ounces. But are we getting, you know, and so there are lots of things you could do. You know, we could try it. You know, 2 pints is 1 quart, exactly. Right, 2 pints in a quart. Should we go that way? No. And so this is the trial and error. The trial and error, this is like, you know, let's say you go on a hike in the jungle and all of a sudden you're lost, right? Are you going to be lost for the rest of your life? Or some people are. They're lost for the rest of their life because what they do is they just leave the page blank and they're like frozen. They can't do anything. But what you should do is, well, it depends if you have enough energy and water or whatever else, food. You should try to, you know, find a path out of the jungle, right? Follow different paths. And so even though, you know, we might mess up, you know, if we go towards the pints, it's actually going to dead end. It's no big deal. We just back up and then try a different route, right? That's what problem solving is all about. Try different things. The more things that we know, the better. You know? And so we might go, you know, rather than quarts to pints or quarts to fluid ounces, we might go quarts to gallons. So 4 quarts to 1 gallon. And then this one's easy because I should know this well or use it. You don't have to have this memorized. There are 3.785 liters per gallon. This one's going to be given. Usually. The ones you should memorize are the definitions. The ones that aren't by definition, I'll give you. But this one's only good to how many sig figs? 4. Which is good for most of us, most of our problems. 4 sig figs is adequate. And then what? Yeah, 1,000 milliliters. Put that on top per liter. So the liters cancel, milliliters are left, gallons cancel, quarts cancel. So that's how many milliliters. And so we punch out the number. Let's see. They have the little trail map here. You know, this is the little trail map. But we don't have to come up with a little trail map. Sometimes we will do quarts to gallons, gallons to liters, milliliters. Sometimes we'll just try to tackle it. If we get lost, well, it's all right. We can do it without a map. Anyway, they did it to 4 sig figs, so we're allowed how many sig figs at the end? Well, this is confusing because how many sig figs do they have here? 2. So really, if they only have 2 sig figs here, we're only allowed 2 sig figs here, which means it should be not 946, it should be 950. But we're doing it exactly, in exactly 1 quart, approximately how many milliliters there are there. And so we should have 4 sig figs here. But do you know what digit they drop? I have no idea what digit they drop because they didn't show me. So this is why I want you to show me so I can see what digit you dropped so I can check your rounding. And so, did somebody do the calculation in their calculator? Do I have the calculator still up here? All right. Okay, I'll just punch it out here. So I'm going to do 3.785, just to streamline it a little bit, divided by 4 times 1,000. 946.25. And so the answer I get here is 946.250. You know, there's no zero at the end, but I'm just going to add it on there because, you know, there are going to be a whole bunch of zeros on the end here on the on your calculator. Your calculator will probably have an 8 to 10 digit display. Maybe it won't show the zeros, it depends. Probably not. And then we're allowed how many sig figs? 4. And so the answer should be 946.3 milliliters. And so if we do it to 4 sig figs, it should be 946.3 milliliters. But you know, their bottle's probably not that. You know, I understand why they said 2 sig figs because it's probably not that precise. You know. It's all right. We're going to be more precise and then rounded.
You guys think you could listen?
I'm sorry?
They're gonna want to give you a little less anyway.
Yeah. Well, will they give you a little less if they round it to 2 sig figs? Hey, you might be able to do that. Hey, you might be able to, nowadays the whole lawsuit thing is the big thing, right? And you might go, well, you know, you said it was 950 milliliters with 2 sig figs. I only got 946 milliliters. Right? But then they would say it's round. If you round it, you know, it's rounding. Rounding's allowed. Okay, next we're talking about temperature. Okay, so temperature, the US is Fahrenheit. The metric world is Celsius. So we have to relate Fahrenheit and Celsius. Is there a simple conversion factor that does it? Like, for example, I told you about the size of the degree. There's a simple conversion factor that does it by delta T. If I go from 0 to 1 degree Celsius, then that would be the equivalent to going from, let's see, delta T, from 0 to 1.8 degrees Fahrenheit. And so Fahrenheit is a little smaller. You know? There are almost 2 Fahrenheits for every Celsius. That we could use as a, but that's for delta T. So if the temperature in this room were 25 degrees C, is the Fahrenheit temperature 1.8 times 25 degrees C? No, because the zeros don't match. If the zeros match, then it'd be very simple. If the zeros match, then we're starting at the same level. If we're starting at the same level, then it would be very simple. You know, all we do is, okay, if it's 25 degrees C, then there's going to be 1 degree Fahrenheit for actually 1.8 degrees Fahrenheit for every 1 degree Celsius. We can do it. But the zeros don't match, so the mathematical relationship is off a little bit. And so what we're going to do is we're going to use the scientific method. What's the first step in the scientific method? Observation. So we'll take our observation. This is our observation. Temperature in degrees C, temperature in degrees Fahrenheit. I'm not even going to do any experiments. If we have 0 degrees C, what's the temperature in degrees Fahrenheit? Is that exact or approximate?
Exact.
Exact. I already know that. If I have 100 degrees C, what's the Fahrenheit temperature? 212. Exact or approximate? Exact. Okay, now we have our data. Well, data sometimes, like a table like this, is hard to visualize. So what do we like to do next? Oftentimes. We try to visualize it graphically by making a plot. If we make a plot, then I'm going to put the temperature in degrees Fahrenheit on the y-axis and the temperature in degrees C on the x-axis. And so if I'm at 0 degrees C, what am I at in terms of Fahrenheit? 32 degrees Fahrenheit. So the first point in our plot is here. If I'm at 100 degrees C, what is my Fahrenheit temperature? 212, so I'll put that up here, 212 degrees Fahrenheit. Which will place it right there. 112. Okay, then I have to come up with something. Like the density of water. The density of water was a curve, like a wave, right? Is the relationship between Fahrenheit and Celsius linear or non-linear? Non-linear would be like a curve or a wave. Linear would just be a straight proportional relation. It's linear. And so we could take a third measurement. We need 2 points to define a line. We need 3 points to define a curve. Well, we need the third point to make sure it's not a curve. And so we take a third point and we see it's not a curve, it's linear. What's the most compact way of representing a plot like this? The most concise way to define a plot like this is via an empirical equation. So what's the empirical equation for this? The empirical equation is y equals mx plus b. This is an empirical equation. And so y we defined as the temperature in degrees Fahrenheit. So the temperature in degrees Fahrenheit, m is the slope. So the slope is delta y. And so what is delta y? It's T final minus T initial. So 212 minus 32 is 212 minus 32 is 180. And so the slope is 180 degrees Fahrenheit. And then delta x is 100, T final minus T initial, 0. 100 minus 0 is 100 degrees C. Times x. X is the temperature in degrees C plus the intercept. What's the intercept? 32 degrees Fahrenheit. So this is the empirical equation that defines this mathematical relationship. But this empirical equation is a bit of too much, and so people simplify this. They just say degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. And so this is the relationship. Or 9/5, you know what 9/5 is? 4 equals, 9/5 is 1.8. You know, 180 divided by 100 is 1.8. Or 1.8 times the degree C plus 32 degrees. And so this is the equation that we memorized here for this. I usually just memorize this one. I don't even memorize. Do you really have to have it memorized? Is this easy to derive? This equation is easy to derive. You don't even have to memorize it. You do the derivation really quick. This is an empirical equation. The same thing, we could do an empirical equation for Kelvin and degrees C. It turns out at Kelvin, 1 degree C is equivalent to 1 Kelvin temperature change. And so if I had a temperature change at delta T of a degree C, then it's the same thing as a Kelvin. You know, so the size of the change, or the degree, is the same. It's actually 273.15. And so we could do this. The temperature in Kelvin, there's no degree symbol here. Temperature in Kelvin is equal to the temperature in degrees C plus 273. Or in other words, the Kelvin is equal to the degree C plus 273. Keep it simple. If you want to be more precise, then you add that little 0.15, 273.15. Here's the 3 scales here. You know, at 32 degrees Fahrenheit, we have 0 degrees Celsius, which is 273 Kelvin, freezing point of water. If you look at the Celsius jump is bigger. You know, it's got to be bigger because in going from 180 steps here to boil water versus 100 steps here to boil water. So 180 steps, the steps are going to be smaller steps.
On the test, you want 273.15?
No, just 273. Very rarely I'm going to ask you 273. We'll just do 273. This will give us 3 sig figs. Most of our answers are going to have 3 sig figs. Convert 288 Kelvin to its Fahrenheit scale equivalent. And so here I would go from Kelvin to Celsius and then Celsius to Fahrenheit. So that's 15 degrees Celsius. And then, degrees Celsius, we just rearrange this equation. Degrees Celsius is equal to degrees Fahrenheit minus 32 times 5/9. That's the way I do it. You can do it anyway. 59 degrees Fahrenheit. So there's a table we convert. So you could try these conversions here. Let me skip this. So I want to talk about proportionality. And so those are temperature conversions. This is algebra. The next thing we're going to go to is density. Density is a ratio, mass to volume ratio, or proportionality. That's what we mean by that. It's just a ratio. This stuff, it's not important. These ratios are used as conversion factors frequently. And so, we can have this. This is just a dimensional analysis written in algebraic form, but I'd just skip that. We just need this. Density is defined as mass over volume. Density is defined as mass over volume. All that other stuff, don't worry about, because I do things the same way. I don't use proportionalities in solving chemistry problems. I use conversion factors solving chemistry problems. Typical units of density are grams per milliliter or grams per cubic centimeter, which is the same thing. So these are the most common units for density. There are other less common units, like pounds per gallon. Pounds per gallon is used. And that involves a more complex dimensional analysis. So we'll look at that. Water, if you take biochemistry, one of the first things you learn in biochemistry is because of the unique properties of water, this is why there's life on Earth. One of the unique properties of water is that the density of the solid is less than the density of the liquid. This is backwards. This is opposite of most substances. The density of the solid is more dense than the density of liquid, which means the solid phase sinks to the bottom. If ice sunk to the bottom, then they say that marine or aquatic life wouldn't exist. Lakes would freeze to the bottom up, and that would be bad. And that's because if you look at the packing, look at the crystalline packing here. What can you say? Is this amorphous or crystalline? That's crystalline. This would be more amorphous. I mean, there's no real structure to it. Everything's more random, although amorphous is usually referring to solids. If we freeze that liquid in time, it's pretty amorphous. Although the water molecules do have structure. Okay? And so, chapter 1 of biochemistry is always water. Density of water, heat of vaporization of water, et cetera, et cetera. Water, of course, is critical for life. This is solid ethanol. How many carbons does ethanol have? 2 carbons. Is this the ethanol? What is this? Grain alcohol or wood alcohol ethanol? This is grain alcohol or sugar alcohol. Although is wood sugar too? Yeah. Where's cellulose? It's a carbohydrate. Solid ethanol sinks. That's weird. Liquid ethanol, I think, was float. Actually, it was mixed. Let's look at some densities. Helium's like the least, 0.00017 grams per milliliter. This is very low density. Air is a lot more dense. Air is a lot heavier. I was wrong about pine. I said pine was 0.4. It's more than 0.5. Maple is a little harder wood, 0.6. Oak is 0.8. Oak's pretty dense. Pine's not very dense as far as wood goes. Water, is that exact or 2? How many sig fig? 2 sig figs. The 2 sig figs were going to be pretty safe for most of the temperatures, except for what? At temperatures, high temperatures or low temperatures, are we going to start to deviate more? at high temperatures. At high temperatures, we probably aren't going to be good with 2 sig figs. It's getting closer to 0.9 something. Glass, about 2.5 times more dense than water, so glass would sink. Aluminum, 2.7 times more dense than water. Iron, 7.8, so iron would rapidly sink. What do fishermen use? You know, people who want their fishing lines to sink to the bottom would use lead, but lead is only 11 times more dense. They should probably use gold.
It's expensive.
Yeah, 19 times more dense. Probably break the line. Yeah, it's much more expensive, but lead has a problem. It's toxic too. You don't want to be touching it with your fingers all the time. Silver is okay, 10 times. Silver and lead are about the same density. Mercury is really dense, but mercury is not a solid. Mercury is a liquid. Copper is pretty dense, 9. In fact, we're going to measure the density of copper tomorrow in lab. It's actually 8.9 something. That's just a 2 sig fig, it's 9.0. And so some densities you should know. What's the biggest density? The smallest? Helium is about 0.1 grams per liter. Methanol. How many carbons does methanol have? 1. It's an alcohol. You can tell it's an alcohol because of the ending. Alcohol ends with OL. 50 milliliter to 4 sig fig sample of methanol is 39.59 grams. Determine the density. And so to determine the density, we just take the mass divided by the volume. So this is mass divided by volume. And then we just get it per milliliter rather than per 50 milliliters. So it's going to be 50 times less that as far as that mass goes. This is wrong. How many sig figs is this? That's 1. 1, maybe 2 sig figs. We're supposed to have 4. And so you need to be consistent because the problems get longer and longer. So you have to write this, even though it's cumbersome, you have to write this to 4 sig figs. Otherwise it's wrong. I mark it wrong. Here we're allowed 4. I want to see 5 because I want to see what digit you drop. They didn't show me, which is... $39.59 divided by 50. So I'm going to just do that really quick. 39.59 divided by 50. 79.18. So what digit do they drop? They drop 0. Even though they drop 0, there's a 0 here. Even though they drop 0, I want to see it. Density of a certain machine oil is 0.910. Will that machine oil float or sink in water? It'll float. It's less dense. And oil and water don't mix. Ethanol and water do mix. So. Find the volume occupied by 196 grams. So what we do is we use dimensional analysis. We need to cancel out grams. And so what we have to do is flip the density upside down. If we flip the density upside down, then the grams will cancel. And then leave us with milliliters, 250 milliliters. Again, I need to see what digit they drop. They didn't show me here. I want to see the drop digit. So you go 4 sig figs and then round to 3. This is multiplication division. We do by the fewest number of sig figs. Okay, now I want to go on to some advanced topics, maybe. So we're going to go on to some advanced topics here. Just take a look. one, have you heard of like linear relationship? Have you heard of like nonlinear relationships? Nonlinear relationships are like squared terms or cubed terms. Like for example, electrical attraction. Electrical attraction is given by Coulomb's law. When we look at the force of attraction or repulsion, the force is going to be proportional to the charge on A and the charge on B, where A and B are being attracted to each other. They have to be opposite charge to attract. If they're the same charge, they'll repel. Divided by the distance between the center of charges squared. And so this is what we call nonlinear. Because if we look at the distance between them, you know, the further apart they are, the weaker the force. And it drops off rapidly. And so what we see is we don't see a linear decline in the force. We see a nonlinear, exponential decline. Like they're close together, the force is very strong, but as soon as they start to get a little far apart, it falls off a cliff. And we have this nonlinear kind of relationship. Well, the same thing happens with conversion factors. You know, we have the linear conversion factors and we have the nonlinear conversion factors. And so, this is what we call nonlinear. Well, we have to think nonlinearly. And so the force is going to dramatically change by curved nature based on distance. So when we look at the force and the distance, it's not linear, it's nonlinear. Okay, now when we're dealing with squares and cubes in conversion factors, CF, so I'm going to call it conversion factors CF, then we deal with those a little differently. So the linear one's easy. For example, if I have a foot, what can I relate a foot to? Inches. So I go 1 foot is equal to 12 inches. And then I want to do 1 square foot. If I do 1 square foot, is that equal to 12 square inches? No, because it's not linear in that way. This is wrong. Do you know what it's equal to? If I do 1 square foot, it's actually equal to 1 square foot is equal to 144 square. Where did I come up with that? Yeah, this is what I have to do. If I want to do it squared, then I have to square the entire thing. And so that means I go 1 square foot squared is equal to 12 squared inches squared. And 12 squared is 144. That's how I got it. How many cubic inches are in a cubic foot? How many cubic inches are in a cubic foot? So if I do 1 cubic foot, are there 12 cubic inches? No. Wrong. Are there 144 cubic inches? No, that's wrong. How many? Well, what I have to do is this. I have to do 1 foot equals 12 inches. I know the linear one. And then I'm going to cube the whole thing. 1 foot is equal to 12 inches. Cube the entire thing. So I'll get 1 cubed. Feet cubed is equal to 12 cubed. Inches cubed. And so is anybody good with cubes? Can somebody just punch it out? I'll do it here. Well, this calculator is not that great. Times 12 times 12. It's 1,728. So 1 cubic foot is equal to 1,728 cubic inches. So this is how we do these nonlinear conversion factors. So sometimes we encounter these. So for example, we want to go from cubic feet to cubic millimeter. I mean, not cubic, square feet to square millimeter. Well, that's easy to do if this were linear, but it's not. So what we're going to do is we're going to start off with 1.0 feet squared. And then where should we go? If we want to get to millimeters, we probably should go from feet to inches. And so I'm going to go this. I'm going to just say 12 inches is 1 foot. We know that's exact. And then just square the whole thing. Okay, then we're going to go from inches to, I would go inches to centimeters. So I know that there's exactly 2.54 centimeters per inch. And then square the whole thing. And then I'll go from centimeters to millimeters. There are 10 millimeters for every centimeter, and then square the whole thing. And so this should give it to me. Let's see what it is. It's going to be, clear that. It's going to be 12. Unfortunately, this calculator doesn't have a square on it. 12 times 12. We're going to multiply it all out. It's 2.54 times 2.54 times 10 squared is 100, so I'll just do that one in my head. 92,903.04. 92,903.04 square millimeter. How many sig figs am I allowed? 2 sig figs. This is exact. So I'm allowed 2 sig figs, 93,000 square millimeter. Or 93 times 10 to the third. Okay.
How would you write the digit that you left off?
I'm sorry?
How would you write the digit that you left off in your answer?
How would I write the digit that I left off like this?
You show your work.
I just showed your work. Or I'd write it like this, 92,000 sub 903.04. The subscripted digits are not significant. The regular digits are, so this shows me 2 sig figs. I usually do this if it's intermediate so I don't lose I don't want round off error. And so if this is an intermediate step, I would keep the digits here so I can continue the calculation later and not lose any information. Or, okay, let's take a look at another advanced problem. 2 more maybe. Let's do number 4. This is from your supplement, by the way. Number 4 is 2.8 pounds per cubic foot to gallons per liter. Or not gallons, this is grams. Grams per liter. They should be grams per milliliter. I don't like that. Unless it's a gas. Gases are typically grams per liter. Like a gas is around 1 gram per liter. But it's all right. We'll just do this. Now this is where we're going to have to do both. We do one at a time. So 2.8 pounds. We don't want pounds. We want grams. And then we want cubic feet. We don't want cubic feet. We want liters. And so we do one at a time. So let's tackle the numerator, pounds. Well, that's easy because that's just one step. 453.6 grams per pound. That's given. It can be given. How many sig figs? 4. So you don't have to memorize this, but it's not a bad one to memorize. The other one to memorize is 2.202 pounds per kilogram. That's also an easy one to memorize with 4 sig figs. All right, so now we got rid of pounds. So we have grams on the top. Now we got to get rid of cubic feet. Now, how can I get rid of cubic feet? I need to go to gallons. How am I going to do that? And so here we might come up with a strategy, or we might just wing it. What do you want to do? Just wing it. Let's see. We need to get rid of feet. So we can go from feet to we could go to feet to yards. We could go to feet to inches. We could go feet to miles. Which one do you think would take us close to liters? Inches? Let's go feet to inches. I'm going to go feet to inches. So I'm going to say that there are 12 inches in a foot. And then what do I have to do? Cube it. But, so I have inches on the bottom. Eventually I want to have meters on the bottom. So I'm going to go from inches to what? Got to get rid of inches. So I'll probably go inches to, well, I could go inches to feet, but I would be going in circles, which can happen if you're lost in the jungle. But it's not a problem if you go in circles because you'll realize it and back up and start over. Or we could go from inches to centimeters. Well, that's about it. So let's try inches to centimeters. So in 1 inch, there's exactly 2.54 centimeters, and then cube it. Now, this, I can go from centimeters to what, or I can go from cubic centimeters to what. And so here's where you have to realize, well, I know a cube. I know cubic centimeters. What's the definition of cubic centimeter? 1 milliliter. So what I'm going to do here is I'm going to go 1 cubic centimeter is 1 milliliter. Right? They're the same thing. Should I cube this whole thing? No. Absolutely not. Do not cube this because a milliliter cube makes no sense at all. And so this is already cubic centimeters, and that's going to cancel that out. And that takes me to milliliters, which means I need to get to liters, which I can go here, 1,000 milliliters per liter. And that takes me to where I need to be. How many sig figs do I want? I only want 2 sig figs to do this here. So I'm going to clear that out. Oops. And then go, well, this is where having a calculator comes in handy, a scientific calculator with a cube key, because you can just cube it quite easily. Versus this calculator. This calculator, they say it's a scientific calculator, but it's not. I should just bring in my calculator. All right, but you know what? I don't want to spend time calculating it. This calculator, you always double check that. What I want to do is I want to look. We're going to just do one more. I'll let you out like 5 minutes early though, I would say, since I gotta go early. But let me just do one more problem. Now, the method is always the same. So what we can do is we can do challenging problems, but the challenging problems are just, you know what makes a challenging problem challenging? It's just longer. And so a challenging problem is longer than, but it's not more difficult. It's just longer, but same level of difficulty. And so let's try a challenging problem. This is from chapter 1 of Chem 1A. Let's do that. And try one of these here. Oh, there's one other problem-solving method, which I should talk about. There's something called 2 equations, 2 unknowns. That's what I'll talk about, or system of equations. Now, I want to develop good habits in you. And one of the bad habits is poor labeling. Number 69 from Chem 1A is impossible to do if you have bad habits. And so let's take a look at number 69. A solution used to chlorinate a home swimming pool contains 7% chlorine by mass. Okay, so what we do in problems like this is we have to know what a percentage is. What is a percentage? 7%. A percentage is what we call a part per 100 by mass. And so what that means is there's 7 parts of chlorine. Now, is that Cl2 or Cl? Normally when we think about chlorine, it's Cl2, but this chlorine could be in the form of bleach. Does bleach have Cl2 or just chlorine atoms in there? Bleach has chlorine atoms, it's hypochlorite. And so what we're going to just do is we're going to say 7 mass units of chlorine for every 100 mass units of chlorinating solution. And so for every 100 grams of chlorinating solution, I have 7 grams of chlorine. For every 100 pounds of chlorinating solution, I'll have 7 pounds of chlorine. I can put whatever mass unit I want in here. Doesn't matter, micrograms, grams, whatever. And so this is what we call 7% by mass. And so percentages are very important conversion factors like density. That's it. Okay, let's go on. An ideal chlorine level for the pool is 1 part per million. And so a percentage is what we call a part per 100. Part per 100. Okay, a ppm is given a different unit. A ppm looks like this, and that's a part per million. And so it's the exact same thing as a percentage, except it's for much lower concentration. And so here we're going to have 7 grams of chlorine. Do you want 7 grams of chlorine for every 100 grams of swimming pool water? You would die, right? It would be way too much chlorine. And so what we need is this. They want 1 ppm, so that means we need 1 part of chlorine. So what we're going to say is 1 gram of chlorine for every 1,000,000 grams of pool water. If we did this in parts per 100, what we do is we move the decimal place 1, 2, 3, 4, 5, 4 places over. If we move the decimal place 4 places over, it would look like this. And so this would be 0.0001 grams of chlorine per 100 grams of pool water. And so what that means is this, it would be equivalent to 0.0001%. And so 1 part per million is the same thing as 0.0001% chlorine. And so what we need to know is these. These are very important. We're going to see these all the time, percentages. We're also going to see parts per million, and we're also going to see parts per billion, parts per trillion. Okay, so we're going to talk more about that, but I'm going to stop here. We'll talk more about the advanced